Okay, in this podcast we're going to talk about Coulomb's law, and as it turns out, there's not much in the textbook on Coulomb's law. However, if you look at the learning objectives for the new curriculum for AP, the Coulomb's law comes up a lot, and it's a lot of the answer to the question why. So there's a one little paragraph in the book, not very well treated. So we're going to talk about Coulomb's law today, and we're going to talk about it a lot during the course. Okay. Very complicated. If you look at these questions and think about them for a minute, my guess is that many of these questions you can answer, right? Which atom is larger, sodium or potassium? Which is has higher first ionization energy, which has a stronger bond? My guess is if you go through those questions, you can answer a lot of those questions. The question is, can you answer why? And if you can answer why, not because of an explanation that involves trends by saying, right-hand side of the periodic table, that's a trend, it's not an explanation. But if you can explain why in terms of attractions, then you know Coulomb's law. Okay? You just might not have called it that. So this is Coulomb's law. And what it says basically is if you have two objects and they have a charge Q1, and charge Q2, and they're separated by some distance that we'll call R, that we can compare the energy required to either break them apart or bring them together as the charge of the first object times the charge of the second object divided by the distance between them. Okay? So we can use this for both attractive forces where, let's say, Q1 is a positive charge and Q2 is a negative charge. They're going to be an attractive force. Okay, and we could also use it if we had two like charges. Let's say they're positive and positive. They are going to be repelled. And Coulomb's law works there too. So let's take a look at how we might apply this in. So if we go back and we look at this model of the atom, where we have a nucleus with some positive charge here, right? And then we have electrons. We might be able to talk about things like, let's say Q1 is the positive charge of the nucleus. And let's say this is a lithium atom, it would have a positive 3 charge. And then we can talk about, what is the Coulombic attraction to something, let's say, like that electron, or to an electron in the first shell. Okay? And so the electron, if we're talking about an individual electron, it's going to have a -1 charge. And if we talk about the distance R gets larger as the energy level or shell moves further away from the nucleus. So what this is saying is as R gets bigger, as that electron is further and further away from the nucleus, it is less attractive to that positive core. And that makes a lot of sense, right? If it's closer, if I have two magnets and I bring them close together, they're going to be a strong attraction. If they are further apart, it's going to be a much weaker attraction. Okay? And it also says things like, if this is an electron, and it's got a negative charge, and the nucleus has a +3 charge, it's going to have a certain amount of attraction. But if this was a nucleus that had a different atom, and let's say it's a positive 10 charge in the nucleus, well, that's going to be a much greater attraction, right? This one negative attracted to a much greater positive charge. So that is essentially Coulomb's law. We're going to use it when we talk about bonding, ionic bonds, in a variety of things, but it's really all about understanding the nature of the attraction and the repulsion. And the two things that impact that are, one is the magnitude of the charges, and the other, that it's inversely proportional to, is the distance separating those charges. Okay, so we know forces this is a little more complex equation you might use if you were in physics, where we're looking at forces and the equation is a little bit different, but it's the same idea. We have Q1 and Q2, and we can use this where we have like charges and they repel, or where we have unlike charges and they attract. Okay? So if we think about this, if we have like charges and they're repelling, and we said E equals Q1, Q2 over some distance R, and we had like charges, is E going to be a positive or negative? Well, if this is positive, and this is positive, and the radius is positive, it's going to be a positive. However, if we're talking about electrons and their attraction for the nucleus, we're going to have some positive nucleus and some negative charge and some electron. And so when I do Q1 times Q2, it's going to be a positive times a negative, so my energy is going to be a negative. Okay. It's actually relatively easy to measure Coulomb forces. You know, you can charge some object and charge some other object with another either like charge or opposite charge, and then measure the distance, the attraction, or how hard it is to pull them together if they're attractive, or how hard it is to push them together if they're repulsive. So it's not a very hard thing to measure, and there's lots of empirical evidence that Coulomb's law works. Okay, so let's imagine that Q1 and Q2 remain constant. What happens if I increase R? Okay, so what happens if, if I increase R, I'm going to be doing this, and Q2 is going to be over here. I'm going to increase R. Well, the energy of attraction is going to go down. Okay, if the particles are separated by some infinite distance, what's going to happen to E? Well, just intuitively, without even looking at the equation, you know that if these are far enough apart, that they are not going to feel the attraction, right? Or feel the repulsion. And of course, if this is infinity in the numerator, in the denominator, then the energy is going to be 0. So let's say the charge of an electron, let's call that Q1, a negative 1, is the charge of the nucleus, and charge of an electron, and Q2 is the charge of the nucleus. So this is a positive, let's call it a positive 1. And R is some finite distance, right? So this is a finite distance, it's not infinite. So what is E? So think about that. Is it less than 0 or greater than 0? Okay, well, it's going to be less than 0 because this is going to end up a negative times a positive, which is going to give me a negative, so it's going to be a negative value. If Q1 for an electron is minus 1, what is Q for a proton going to be? Think about all these. Q for a proton, a neutron, and the nucleus of a carbon atom. Okay. All right, so for a proton, if an electron has a charge of minus 1, a proton is going to have a charge of plus 1. A neutron is not going to have any charge. It's going to be 0. And the nucleus of a carbon atom is going to have a plus 6. Okay, when we're talking about energy, so what kind of energy are we talking about? Well, we're really talking about ionization energy, which is also sometimes called binding energy. It's the energy in which this electron is attracted to the nucleus. Okay, so the actual definition of ionization energy is the energy required to remove an electron, right? So I have some atom and I remove the electron. So that's basically the equation for it. I have an atom, I remove an electron. How much energy does it take to do that? Now, anytime you separate something, you break a bond, or you remove an electron, you are requiring that you put energy in. So this is an endothermic process, requires energy. Even if it's, we say things like sodium wants to lose an electron. Well, in fact, it still does take some energy. Okay, so the ionization energy is the energy required to remove an electron. So that's the energy we're talking about. Okay, so let's think about this. Which of the following would have the larger ionization energy? Take a minute and think about it, but take your pencil out and jot down mathematically how you could figure this out. Okay, if I were to look at scenario 1, and here's my equation, E equals Q1, Q2 times R2, over R. And so for number 1, my energy is going to be equal to an electron, which is going to be a -1 charge, times a nucleus with a +2 charge, over this distance R. So this is going to be a -2 over R. And if I look at number 2, this is for number 1, and for number 2, it is going to be, again, an electron is -1. Now it says the nucleus has a +1 charge, and that is going to be over distance of 2R. So this is going to be a -1 over 2R, or a 0.5R. So what you can see here is this is going to have be a factor, a magnitude of 4 times greater than this. So this is going to have a higher ionization energy required to remove that electron. All right, so let's take a look at this one. Go ahead and show the math, figure out which one is going to have the higher ionization energy. Okay, for number 1, it's going to be an electron, -1, times a +6 nucleus charge, over 5R. And that's going to be -6 over 5R, which comes out to be 1.2 over R. 1.20 over R. If I look at the second one, it's going to be a -1 charge times a +7 charge over a 6R. And this is going to be a -7 over 6R. And that's going to come out to be 1.17 over R. So the first one is going to take just a tiny little bit more energy. You can even argue that it's insignificant from a sig fig standpoint, but it's going to take a tiny bit more energy. Very close. All right, so think about this. If I have an electron with a charge of -1, okay, very close to a nucleus with a charge of +2, is the potential energy going to be large or small, positive or negative? So think about that and then come on back. Okay, so they're very close together. They're positive and they're negative. So I'm going to call that charge or the energy positive, very attracted to each other. And because this is a plus times a minus times a plus over something, some distance that is going to be positive, it's going to have a negative sign. So the answer is going to be B.